So pick back up. So we're going to compute the probability of observing a full house. Right, so just a reminder, so a regular deck has 52 cards. There are 4 suits and 13 ranks. The 4 suits are hearts, diamonds, clubs, and spades. The ranks are ace through king. A full house consists of 2 of one rank and 3 of some different rank. Okay. So all of the different poker hands, right? So I'm going to take the 52 decks and deal 5 cards. All of the possible hands are equally likely. So what we're going to do is take the number of events in which I have a full house, right? So there are lots of different ways to have a full house. I'm going to count the number of ways to have a full house, and I'm going to count the total number of hands, and then I'm going to divide the number of ways to have a full house by the number of hands, and that's it. Okay, so this is our kind of our discrete uniform probability. Count the number of events in the sample space, which in this case is the total number of different hands I could have. And I want to count the number of those events on which I have a full house. Okay, so let's do the easy part first with the denominator. Okay, so poker hand. So I want to do, is there a replacement, and does order matter or not? So order doesn't matter. Right, so having ace, 2, 3, 4, 5, all of hearts in that order is the same as if somebody deals me 5, 4, 3, 2 ace of hearts. Right, so so the hand that I get doesn't depend on the order in which the cards were dealt to me. So order does not matter here in what hand I ultimately get. And there is no replacement. If you deal me the ace of hearts, I'm not going to see the ace of hearts again when you deal the next card. So when you deal a card, it's dealt, and it's not going to come up again for the next card that you deal. So order doesn't matter, and I'm doing no replacement. Okay, so that's the choose scenario. So the total number of hands is 52, choose 5. Right? So 52 possible cards. How many different hands could you have? Let's choose 5 of those 52 cards. That's it. That's our denominator. That's the easy part. So here's where we have to be very careful, because I'm going to choose in stages and to figure out the total number of different ways to get a full house. But you have to be very careful about these stages, because you don't want to count things more than once. So I want to choose things in stages, but this choosing things in stages has to have the following important property. If I make a different choice at any stage, right? So I'm going to say I'm going through and I'm choosing at the stages, and maybe someone else is going through and choosing at the stages as well. If they make a different choice than I do at any stage, then we shouldn't end up with the same final result. Okay? That is the correct way to use this choosing in stages. So the first thing I'm going to do is I'm going to choose. So I have to choose one rank to have 2 cards of, and then I'm going to choose the other rank to have 3 cards of. So let's say, how many ways are there for me to choose whichever rank I'm going to have 2 of? Okay, so so there are ways to say 13, choose 1, which is just 13. Ways for me to choose the rank such that I'm going to have 2 of those, 2 of that rank. So for example, if I have, say, ace, ace, and then queen, 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 right? So here I chose ace, ace, but there are 13 other things that could, or 12 other things that could have chosen here instead of ace, right? So what I'm doing now is I'm choosing with the rank that I'm going to have 2 of, and there are 13 ways to do that. Okay? Now, I've chosen the rank, so here, let's say I chose ace, right, just for a concrete example. So maybe in stage 1 I chose ace, and now I need to have 2 aces, right? So there are 4 aces total. How many ways are there to choose 2 of them? There are 4 choose 2 ways to choose the 2 aces that I'm going to have. So it could have ace of hearts and ace of diamonds, ace of hearts and ace of clubs, ace of hearts and ace of spades, or it could have ace of whatever, you know. So, and there are 4 choose 2, which is 6 ways to pick a pair of aces. Right? These are four aces. There are 4 choose 2 ways to pick a pair of those 4 aces. Right? So now I need to figure out. So I chose in this particular concrete example, I chose an ace, and then I picked 2 aces to have my pair. Okay. Now I want to choose the rank that I'm going to have 3 of. Okay. So up here, I chose a rank. Okay. So now here, the rank that I'm going to have 3 of has to be a different one than the one I chose in stage 1. Right. So if I chose ace up here, I cannot choose ace again in stage 3. If I choose king in stage 1, then I cannot choose king again in stage 3. So now when I'm going to choose what rank I'm going to have 3 of, there are 12 ways for me to do that. Okay, so 12, choose 1. Okay, so the 12 that I'm choosing from are the 12 remaining ranks after I take out whatever rank I chose in stage 1. Okay. And now I have to choose 3 from that rank. So here in this concrete example, let's say this one is a queen, right? So now there are 4 queens in the deck, and I have to choose 3 of them. So that's 4, choose 3. Okay. And I'll leave it to you to figure out that if you choose, you choose something in stage 1 and 2 and 3 and 4, and someone else makes a different choice in any one of those 4 stages, they're going to get a different hand than you, right? So with all these choices, I'm not double counting anything. And the total number, so I have this many choices in stage 1, then after that I have this many choices in stage 2, and then after that I have this many choices in stage 3, and then after that I have this many choices in stage 4, so the total number of ways to have a full house is this. Okay. So the total number of ways to have a full house is this. Total number of hands is this. So my final answer is 13, choose 1. 4, choose 2. 12, choose 1. 4, choose 3. Over 52, choose 5. And I'm not going to do any simplification. I'm not going to do anything other than I'm going to write it like this. That's going to be my final answer. And I prefer you leave your answers like this. Right? So 13, choose 1 is 13. 4, choose 2 is 6. 12, choose 1 is 12. 4, choose 3 is 4. Right? So, I mean, maybe you can actually multiply this out, and the numerator is not too bad. Denominator is probably not even too bad in this case. But there's no reason to rewrite it. I mean, any one of us could go, get on a computer, get a calculator, whatever, and actually figure this out. We don't need to. Okay, so leave it like this for quizzes, tests. That's good enough. Okay, so there's my answer. Okay, so here's a more involved choosing in stages, and you have to be careful. Okay, so one of the areas I had to be careful here was here I'm choosing a rank to have 3 of, and I have to choose something different than the rank I chose to have 2 of. Right? So there are only 12 possibilities here because I chose a rank here, and here I have to choose one of the remaining 12 ranks. Okay, so this is this type of problem. I really enjoy this type of problem, and it can be some subtleties in this type of problem. Right? So another important distribution, another important type of situation would be, let's say I have a total population, and the size of the population is m plus n. And m of those objects are from some class of interest, and the other n objects are from outside the class of interest. So, for example, let's say I am a washing machine manufacturer, right? And I produce a big set, a big shipment of 10,000 washing machines, right? And I know that some of those washing machines end up being defective, right? So let's say I have, just for example, I have 20 defective washing machines, and then the remaining 9,980 would be non-defective, right? And so m here would be 20, and then n would be the other 9,980. So I have all my washing machines as the total population, and then I have 2 subsets, the defective and the non-defective, right? And I'm interested in knowing how many are in each. Okay. So that's the situation. Okay? And if you're actually doing some like process control, you might really care about this. So this literal example of figuring out how many of your washing machines are defective. If I have a high number of defective washing machines, I need to fix my production process. Okay? So m objects from a class of interest and n objects that are not in that class of interest. So which class is the class of interest doesn't matter. This is going to be a symmetric problem. Right? So I could say the defective ones, that's the class of interest, and the non-defective is not the class of interest. But if I said the non-defective is the class of interest and the defective is the non-interest, right? Doesn't matter. Doesn't matter if I switch. Like, it's a symmetric problem. So which class is the class of interest doesn't matter. Okay? So I'm going to pick I plus j objects from my total population, and no, what's the probability that I of those are in the class of interest and j are not. Okay, so I want to know, let's say, and this is a kind of a slightly realistic, although probably idealized version of a real world problem. I can't test all 10,000 washing machines to see if they're all, if I have an appropriately low number of defective washing machines, right? So maybe I say I can have 20 washing machines that are defective. If I have more than that, I have to fix my production process. If I have 20 or fewer defective washing machines, then my production process is fine, right? But I can't test all 10,000 of them. I can't test every single washing machine. It's too many. So what I can do is say go test 100 of them, right? So I'm going to go pick 100 washing machines, right? So here, 100 is going to be I plus j. And I'm going to see, well, out of the 100 I picked, one of them was defective and 999 were not. So 99 were not. So I pick 100 and one of them was defective and 99 were not. So here I would be 1 and j would be the other 99. Right? So I want to know what's the probability that if I pick I plus j objects, I of them fall into this class of interest and j falls outside of the class of interest. Right? So here obviously we're going to be subject to I has to be between 0 and m. Okay. M is the total number of items in the class of interest. I can't have more than that. Right? And j has to be between 0 and n, where n is the number of things not in the class of interest. Right? So here, so we have a big, all of the washing machines, and then over here we have m, which are non-defective, and n, which are defective. I want to reach in and grab a sample, and I want to know, I'm going to get, of the washing machines that I get, I'm going to say, well, one of them was defective, so I would be 1, and 99 were non-defective, so j is going to be 99. I want to say, what's the probability that that happened? Right? And so the kind of key thing of interest here is I know m plus n, but I don't know m and n, right? So in this scenario, I said maybe 20 that were defective, but in reality, I wouldn't know how many are actually defective. And what I would want to do is say, well, let's see what we actually observe, and is this consistent with having 20 or fewer non-defective washing machines, right? So that's it. In the applied scenario, that's how one would actually use this. But then I want so we're going to do hypothesis testing and interesting things from statistics that we're not going to talk about. This is what I can do is say, this thing that I actually observed, is it consistent with the null hypothesis that I have 20 defective washing machines, right? So all I really want to know is how to account this. So assuming I have m objects in the class of interest, m defective washing machines, and n outside the class of interest, so n non-defective washing machines, and I reached in and I grabbed I plus j many washing machines, and I of them were defective, j of them were non-defective, what's the probability of that outcome? Okay. So we're going to do, reaching in and grabbing, right, all of the pairs or all the subsets of I plus j things that I could grab are equally likely. So I'm reaching into a set of m plus n objects here, and I'm going to grab I plus j of them. How many different outcomes could we have? Well, I have m plus n things, and I'm choosing I plus j of them. The total number of things that I could grab is this denominator. Okay, so there are m plus n total objects. I'm going to reach in and grab I plus j of them. There are this many ways I could do that. M plus n, choose I plus j. So, how many ways are there for me to reach in and choose I things from this first category and j things from the second category? Well, the first category has m things in it. So there are this many ways for me to reach into the category of m things and choose I of them. And the second category has j things in it, or n things in it, and I reach in and I choose j. So here I'm choosing in stages. Stage 1 is reach into the first category and choose I things. Second stage is I reach into the second category and choose j things. There are this many options I have on the stage 1 and this many for stage 2, and multiply those to get the total number of ways to reach in to this population that has m things in group 1 and n things in group 2, choose I plus j things, and have I of them from group 1 and j of them from group 2. So that's the hypergeometric distribution. So I'm going to be a little more specific here. So m and n are parameters of the distribution. So in this problem, I'm going to ask you, well, you might be asked to compute probabilities, and in this problem, m and n are not changing. M and n are fixed. Okay? So what you would be asked for is, given a specific value of I and j, compute the probability. M and n are fixed, I and j are varying within the population. Okay? So the m and n are not variables here, they're parameters of the population. The I and the j are variables here that can change. Right? here's our formula. And the derivation of the formula is, again, pretty simple. So I'm going to reach into this population, which has this many things, and I'm going to choose I plus j things. There are this many ways to do that. Okay? Now I want to know what's the probability that I reach into the first population and grab I things, and reach into the second population and grab j things. Well, there are this many ways to reach into the first population and choose I things, and this many ways to reach into the second population and choose j things. So this times this many ways to do both of those. And that's the hypergeometric distribution. So now we're going to move on to Bayes' rule and conditional probability. In probability, oftentimes we can assume that we know that some the outcome is going to be in some sub-event, right? We have some event here, and we are only concerned about what's happening in that event. So what we're going to do is say S is the total overall sample space, set of all possible outcomes, but I really only care about this subset B. So what I'm going to do is I'm going to take this subset B, and I'm going to zoom in on it, and then I'm going to create a new probability where my total universe, my total sample space is just B. Right? I don't care about outside of B anymore. I just zoom in and I forget all of this and just look at B. Right? Now, A is going to be some event in the original probability space, but I'm really going to only care about, okay, if I know that B already happened, what's the probability that A also happened? So here, right, over here, this is A intersect B, but when I zoom in and only care about what's happening in this B box, it just looks like this. Okay? So, you might say, so S would be, say, set of all combinations of you studied for the final or you didn't study, and you passed or you didn't pass, right? So there'd be like 4 outcomes: studied and passed, studied and didn't pass, didn't study and passed, didn't study and didn't pass. Those are my 4 outcomes. And I might say, let's let B be the event consisting of the outcomes in which you studied, right? So B would be you actually studied. And then outside would be you didn't study. Okay? We might not care about what happens when you don't study because we know you're going to study, right? So we just zoom in and look at the studied situation, right? And so maybe A is the event that you passed, right? So B is the event that you studied, and A is the event that you passed, right? So if I say, given that you studied, what's the probability that you passed? And so I don't really care about what's happening outside of this B box because that's you not studying. B is the event that you studied. A is the event that you passed, and then A intersect B is the event that you studied and passed. If we just look at the B, which is given that you study, then this A intersect B would be you studied and passed, and then the remainder would be you studied and didn't pass, right? So the reality, event B should be most of it, right? Probability that you study for the final should be very high. And over here, this non-shaded part should be very small, because if you study, the probability that you pass the exam should be pretty high. Right? So, so the way that we write this is probability of A given B. So this bar means given. This A is the, we're going to say, event of interest, and B is what we call the conditioning event. Okay, so this is red, the probability of A given B, right? And so we could say A is passed the test, and B is studied. And this would be, what's the probability that you passed the test given that you studied for it? Right? So like I said, the whole thing is, initially, this whole thing is some probability space. What we're doing is we're zooming in and just ignoring everything outside of the box, but we want this to be a new probability space, right? So, well, the probability of so the thing about a probability space is the probability of the whole sample space has to be 1, right? The probability of observing an event in the sample space is 1. That's by definition of the sample space. All the possible outcomes are in there, so the probability of observing one of those is 1. Okay, so here, if I just look at the probability of B, it's not necessarily 1, but we can fix that. Okay. So, by definition, okay, the probability of A given B is the probability of A intersect B, which is the shaded region here, divided by the probability of B. And this only makes sense if the probability of B is positive, right? So I can only do this definition for events B such that the probability of B is positive, not 0, right? And now I'm defining this. So now I can define this new thing, right? So I'm going to put a, right? So this I think of as being a new probability, and I put events in here, and the definition is this, right? And then you can confirm that it defines a probability on this sample space. Okay? So this formula is defining a new probability where kind of this dividing by b normalizes this so that the probability here, if I put b here, it's the probability of b over the probability of b, which is 1. So kind of I just divide by the probability of this to make it 1. And now I can look at the probability that I studied, or the probability of the past given that I studied is this. And so this is our formula for conditional probability. And now we can use Bayes' rule. So assuming I have two events with positive probabilities, then, well, just taking this, so taking this equation, multiplying both sides by the probability of b, I get the probability of A intersect b is the probability of A given b times probability of b, which is what's written here. Right? So here I could think about this as another choosing in stages problem. Right? So probability of A intersect b is, well, probability of b, and then I say choosing b or not b in stage 1, and in stage 2 I just zoom in on b and choose A intersect b or b take away A. Right? So kind of a stage 1 I'm going to choose to be inside or outside of b, and then I'm inside with probability p of b. And then once I do that, I choose to be either in A intersect B or not, and that happens with this probability, given that I chose to be inside of B in stage 1, right? So this is a very nice interpretation in terms of stage 1, stage 2. Right? So, well, there's a symmetry here. Probability of B given A times probability of A is also this. Right? So just go up here, reverse all the A's and B's, and you get this. So then our probability of A intersect B, or A, not A intersect, A given B is probability of B given A times probability of A or probability of B, and I find that by taking these two things and solving for probability of A given B. Just divide both sides by probability of B, and I get this. And this is, well, this is one form of Bayes' rule. Okay, named after Thomas Bayes. So let's look at an example how we might use this. So let's say the probability of studying is 0.6, and the probability that you pass, given that you studied, is 0.9, and the probability that you pass, given that you didn't study, is 0.5. Right? So in reality, I think that the 0.9 is an underestimate. If you study, I think there's a lot higher than a 90% chance of you passing. And I think if you didn't study, who knows? This might be an overestimate. And now let's look at probability that you say you pass the test, and you might ask retrospectively, what's the probability that the person didn't study, right? So you know somebody passed. What's the probability that they didn't study? Right, so we can use Bayes' rule for this together with this given information. So probability that, so let's let A be the probability that you didn't study, and B be the event that you passed. So the probability of A given B is probability of B given A times probability of A divided by probability of B. Right? This is our formula over here. So now I'm going to put in these specific choices of A and B. A probability that you pass given that you didn't study. Well, we know that. It's 0.5. Okay? Times probability of A, which is the probability that you didn't study, divided by a probability that you passed. Okay? So now I just need to fill in these three pieces. Okay? Probability that you passed, given that you didn't study, that's given, that's 0.5, so I put a 0.5 here. Okay? The probability that you didn't study, well, that's not given, but the probability that you did study is 0.6, so the probability that you didn't is 1 minus that. So 1 minus 0.6. Okay, the only options are you studied or you didn't. Probability that you studied is 0.6, and probability that you didn't is 1 minus that, which is 1 minus 0.6, which is going to be 0.4. And now we have to know the probability that you passed. Okay, so that one we have to figure out. Okay, so let's figure that out. So the probability that you passed is, and here's a very standard technique. Okay, so this is important, and this uses our probability of disjoint events. So the probability that you passed and studied or probability that you passed and didn't study. Okay, so if you pass, then either you passed and studied, or you passed and you didn't study. Okay, that's it. Okay, so passed and studied is disjoint from passed and didn't study. right? So it's not possible for me to be in this event and this one. It's not possible for me to have studied and not, right? So because of my probability of disjoint events, this is the probability of passed and studied plus the probability of passed and didn't study, right? Just because I'm unioning two disjoint events here, right? So the thing in the box is one event, the thing in this box is another event, and the things in those two boxes are disjoint because it's not possible for me to have studied and not studied, right? So the probability of passed and studied is the same as, so remember this is using my conditional probability distribution again, so I'll take this, multiply by probability of B. Probability of the intersection is the probability of A given B times probability of B, right? So I want to do probability pass given that you studied, so probability that you studied, right? And this is equal to this, just by the definition of probability you passed given that you studied. Over here we're going to do the same thing. It's probability that you passed given that you didn't study times the probability that you didn't. Right? And I know all four of these numbers. Probability that you passed given that you studied, 0.9. Probability that you studied is 0.6. Right? It's 0.6. Probability that you passed given that you didn't study, that was given as 0.5. Okay? And the probability that you didn't study is 0.4, right? 1 minus 0.6, so 0.4. So this is my probability that it passed, and here I'm using a few different things. Right? So I take the pass and split it up into two disjoint events, and then separate. Okay? And now I use, in order to compute probabilities of intersections, I use the definition of conditional probability, and now I plug in given information. Right? So everything on all four of these things on this line, that information is contained in these three given pieces of information. Okay? So this is probability that it passed. Okay? So I'm going to have 0.9 times 0.6 plus 0.5 is 0.4. Okay. So this is it. I didn't actually work this out. Hopefully it's pretty small because, well, I want you to study and I want you to pass.